So welcome back here, guys, to lecture number 12 from Math 122. Um, this is a pre-recorded lecture, and we will be continuing with rational functions. Last time we left off on graphing rational functions. We started to see that this matter of vertical asymptotes and horizontal asymptotes are basic and fundamental characteristics of a graph of a rational function. And we also see how closely related vertical asymptotes are to the domain and how horizontal asymptotes are closely related to the range. And we also see how the intercepts are useful ways to know in a way, where the graph would go. Um, as we venture into rational functions, we have seen how complicated graphs can be, especially when you compare them to the nicer, tamer, smoother, connected functions such as polynomial functions that we've discussed before, to rational functions. Um, and we've also discussed, for example, how we can determine end behavior by the degree of the numerator and the degree of the denominator. And we also found out ways to find the vertical and horizontal asymptotes without even having to do much in terms of understanding what the graph is. We can find what vertical and horizontal asymptotes the rational function may be just by looking at the kind of function it is, symbolically, of course. And we saw how certain rational functions are just transformations of the parent function 1 over x. And so and this is what we've been venturing into, um, this idea about how x values approach certain x, how there's certain x values that we're approaching and how that affects the y values. These kind of this kind of expression or ideas, uh, they start to get closer and closer in line with what you will see for those of you who continue in calculus, especially when you talk about limits and those are like introductory topics in calculus. This is where you guys are starting to develop that foundation when you get to that level. And rational functions as a whole is definitely very much studied and especially in calculus, and so it's worthwhile to go through as carefully as possible, um, to understand graphing rational functions, understand its end behavior, understand where it goes wrong with the domain, understand how that affects um, the domain and the range and the asymptotes. And so, yeah, so that's what we've been on so far. Okay. And this is a PDF that I have uploaded on Google Classroom, so you guys can check it out. We'll be continuing along with this PDF. We're almost done with it. So let's look at this next example of rational function. So we have r of x equals 3x squared plus 6 all over x squared minus 2x minus 3. And there's a little typo here, so you guys can fix that. It should say horizontal, not slant. We're not there yet. So that's a typo. It's a horizontal asymptote. So those are the first few things that, even though it's at the bottom of these bullet points here, it's kind of the first thing most likely that you'll have to figure out, Because once you figure these things out, then you can figure out the domain and range. So the asymptotes, again, the vertical asymptotes are the cases where occurs where the x value makes the denominator equal to 0. And so therefore we find those x values that make the denominator equal to 0 and say that those are the x values that that are not in the domain. And so therefore those represent the vertical asymptotes. So the vertical asymptotes occurs when the denominator equals 0. So I'm going to set my denominator equal to 0. What I notice is that this denominator equals 0 and it's a quadratic. And I can factor this quadratic by finding two numbers that multiply to -3, but that add to -2. And the only one that makes sense is -3 and +1. And in this case, the result is that x minus 3 equals 0, of course, and x equals +1 equals 0. So therefore, x equals -1 and x equals 3. So in this case, we get two vertical asymptotes. So we have plural. That can happen. We can have many more. It's possible to have an infinite number of vertical asymptotes. One kind of function that we'll discuss later in the semester when we talk about trig is tangent functions. Tangent functions have an infinite number of vertical asymptotes. In this case, we have two x values that make my denominator equal to 0, and so therefore we have two vertical asymptotes, and rational functions could have more than one vertical asymptote. So what do we write? We write x equals, for the vertical asymptotes, x equals 3 and x equals -1. Okay? So that's what we have for our vertical asymptotes. And then we notice, let me just plot that real quick. So -1, I'm going to give it these boundaries here, this dotted line. So this represents x equals -1. I'm just going to write this as vertical asymptote. X equals -1, and then add 3. 1, 2, 3, right? So this, and this is a vertical asymptote, x equals 3. Okay. And so the vertical asymptotes will affect the domain. And so we see that all the x values are good, but we have to skip -1. Then everything in between here is good, but we have to skip 3. And everything outside of 3 is good. So then the interval notation would be -infinity to -1 union, -1 to 3 union, 3 to infinity. So again, the vertical asymptote affects the domain. Now let's look at the horizontal asymptotes. Remember, the horizontal asymptotes are determined by first identifying what the degree of the numerator and denominator is. So we know the degree of the numerator is the highest exponent, which here is 2. The degree in the denominator, the highest exponent here is also 2. So because the highest exponent for the numerator and the denominator are both equal to one another, then remember we talked about those three cases for horizontal asymptotes. This is the case where the both the numerator and denominator have the same degree, and because they have the same degree, then the y asymptote, pardon me, is the ratio between the leading coefficients of the numerator and denominator. In this case, the leading coefficient of the numerator is a 3, and the leading coefficient of the denominator is a 1. So we say that the horizontal asymptote is y equals 3. So y equals 3, we'll put that somewhere here, y equals 3. Okay, and then horizontal asymptote is going to affect the range. The range are the y values. And so I think for this one, we do have to be a bit careful, a bit careful. So I'm not going to jump into the range just yet. But we have to check something out. This one, so because it has more than one vertical asymptote, then sometimes things can be get a little weird with the shape and the way the graph works. So before we go into the conclusion of the range, let's look at the x-intercepts. Remember, the x-intercepts occur when the numerator equals 0. So x-intercepts occur when the numerator equals 0. I'll put this over here. So the numerator has to be set equal to 0. 3x squared plus 6. This equals 0. But if you notice, this has no solution. There is no x value that when you square it and you multiply by 3 and add by 6 will give you a 0. If you don't believe me, you can try to continue. You can say 3x squared equals negative 6. So therefore, x squared equals negative 2. And then say that x is equal to plus or minus the square root of negative 2. But that we run into a problem because now we have a negative underneath the square root. And so this indicates complex numbers, but we're in the plane that uses real numbers. So that's why we say that there is no solution to this equation, no real solution, I should say. And therefore, there are no x-intercepts, so we say there are none. And then the next question says, the y-intercept. What is the y-intercept? I'm going to write this in blue. And remember, the y-intercept, so x-intercept is when y equals 0. The y-intercept is when x equals 0. So what happens when you plug in 0? This is for the y-intercept. If y equals 0, what do I get? I get 3 times 0 squared plus 6 divided by 0 squared minus 2 times 0 minus 3. So this equals 6 over negative 3, which is negative 2. So the y-intercept is 0, comma, negative 2. Okay? Okay. Now, we have to be a bit careful with the range. And why is that? So we know this goes at 0, negative 2, right? We know that this touches it at this point. If this is a negative 2, we say this is 0, comma, negative 2 is the y-intercept. And we say that we have no x-intercepts. So let me see if you see the rest here. Okay, yes, you do. So I'm going to graph this using a graphing calculator. So 3x squared plus 6x, and then we have so 3x squared plus 6, and then we're going to divide this by x squared minus 2x minus 3. So look at this. So this is when you start to see how, at least in the previous examples last class, the 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 graphs tend to be kind of the same style. We have one vertical asymptote, we have one vertical horizontal asymptote, and it was kind of clear as to what was gonna occur with the graph, because it was just a transformation of the graph 1 over x. But the problem starts to become when we get these kind of things where we have higher degree polynomials for the numerator and denominator, and our vertical asymptotes are more than just one vertical asymptote. So what's the issue that I'm referring to? I'm referring to the following. So if you notice, there is a break, right, within the green curves. Uh, you notice that at -1, it is indeed a vertical asymptote, right? And we also notice that at 3, so if you're at 3, you notice that it's also a vertical asymptote. So there's a break here, right? There's a break. Um, it's not a connected curve. It's not a connected curve. You have one piece of it up here, we have another piece of it below, and then another one to the right. So that's okay. And the asymptote, however, that's horizontal, if you remember, we found that it was equal to 3, correct? And if you notice the graph at 3, if you notice 3, the graph actually cuts through. It cuts through, and then the graph starts to get closer and closer to 3, but not actually touching it. So I know this sounds a bit strange to say, but I remember how I introduced horizontal asymptotes. Um, I guess one way to first bring it to your attention is to say that it's a horizontal line wherein the graph never touches, or it gets really close to it, right? It approaches it. Um, so the asymptote is more of a boundary when we consider the ends at the ends. In reality, horizontal asymptotes, for example, you can cross them, you can touch them, but that occurs not at the ends, I should say. So if you notice at the end, both of these graphs, you see, both of these graphs, they get really close to it but never touches it. But there's this part of the graph that does cross at y equals 3. It does cross it, but that's only not at the end, near the center, you can say. But at the end, as you start to see, these lines get closer and closer to that asymptote. That's one thing that might seem a little strange. Another thing, because of that, right? Then you start to ask yourself, well, what would you say for the range? So the range can be a bit complicated because of this. What is the range? The range is the smallest. It's not the smallest. The range is all the y values, correct? So you see that we know for a fact that at 3 there's an asymptote. If you look at this curve on the right, it never crosses 3. So it's always bigger than 3. But this left side, for some reason, does cross 3. So 3 is attained. And you see this graph here, this from right to left, you see how it goes down? It dips, but then it starts to come back up. But of course, now it doesn't cross 3. It gets really close to 3. So this point, the way this GeoGebra works is that they give you those points already. They're called extremum. So they're called the points that are either called local mins or local maxes, right? So this is the smallest point on these two graphs, portions of the graph. And you see here, this is negative 5.37, and this is 2.529. So you can see that out of the first two, out of the left curve and the right curve, the smallest or the boundary for the y values occurs. I think I just lost it here. Let me regain it. Yeah. So this point right here, negative 5.372 to 2.529. So then if you compare those two, if you compare these two portions, the left portion, the green portion, and the rightmost portion, the green portion, the smallest y value is the y coordinate of this point, 2.529. So I'm going to write that. So that means that everything above 2.529, everything above this is part of the um, graph. That's the range. But then we notice as well that there's a middle portion here, and the highest y value here is at negative 1.779. And then, so there's this gap between this point and this point. This is the smallest point for those first two graphs, the first and the last graph. And this is the highest point of this middle graph. So there's a break in between the two, and this is negative 1.79. So this is going to be negative 1.779. And I'm going to union that. This goes to negative infinity. Now, and then pardon me, I also include it because those are points. So I include those points as well. So I agree. This kind of range can be tricky. And then how do we do this? Well, if you were to use calculus, you would be able to figure these things out a little bit better. But in general, rational functions aren't that simple. So to give you the sketch, we actually need the graphing calculator to help us. And we see that negative 1.779, right, is the highest. So it's going to be negative 1.779. And let me just go back and see. It's like around 0.3. So 0.3 is somewhere here, and this is negative 1.79. So somewhere right here. I know that my graph goes up here and then it comes back down. It never crosses the x-axis, right? We know that, x-intercepts. And then we know that this curve here kind of moves like a normal rational function curve would do, right? It gets close to the vertical asymptote, it gets close to horizontal asymptote. It's just that this one here does a very strange dip past the crossing the horizontal asymptote. And then this point here is the smallest it could be. This is the smallest, and this is the maximum of that curve. And so that's why how we get our range, because of this kind of setup. And of course, the best way to graph such a function is to use a graphing calculator. So your graphing calculator will be a great asset for these things. Okay, so this is the general template of rational functions. We figure out the vertical asymptotes, the horizontal asymptotes. That then in turn affects the domain and the range, and the x-intercepts we can find as well, along with the y-intercept. And so that helps us give us an idea of how the graph may look. It might be more complicated than we think, so graphing it using a graphing calculator will definitely help you get the general idea, because as you start to see, rational functions don't all behave very nicely the way you saw in the previous several examples, right? Where they're just portions on one side or the other of the vertical asymptote and of the horizontal asymptotes. Okay, so now we're going to get to the interesting cases, also known here as special cases of rational functions. And so for the first one, we're going to be considering rational functions that have quote unquote holes. And this is an important topic as well, because that's going to come up in calculus, especially when we talk about limits, you're gonna have these holes, quote unquote. Now, what do I mean by this? Well, let's look at this rational function again, and before we continue, uh, we should see something about this rational function. The numerator can be factored as x minus 6, x plus 1 over the denominator is x plus 1. So what is this? Don't the x plus 1s cancel? And what do you get? You get x minus 6. So r of x is really x minus 6. And what kind of function is x minus 6? Isn't x minus 6 a linear? It's a linear function. So I can just draw a line. There's just one tiny problem. We were able to divide the x plus 1 with the x plus 1 under the assumption that x plus 1 is not 0. Think about it. You can't have 0 and a 0 and say cancel out the zeros. That's not how zeros work. So already x plus 1 was an issue in the beginning because x plus 1 would make the denominator 0 if x were to equal negative 1. But the difference now in this case, right? Normally we would say, oh, x equals negative 1 is a vertical asymptote and move on. But the problem with this, so the key observation, so the key observation is that the for holes to exist, okay, for holes to exist, there must be a factor in both numerator and denominator that are the same. Okay, so they must be the same for holes to exist. Save these. Well, it's okay. So x plus 1 is factored in both the numerator and denominator and are canceled, but this cancellation only occurs. So this cancellation is only permitted if x plus 1 does not equal 0. So it can't equal 0. X plus 1 cannot equal 0. It could be anything else. So the problem is when x equals negative 1. That's the problem. So we can only say that the rational function is equal to x minus 6 when x does not equal negative 1. Now, when I go to graph this, this is gonna look like x equals 6. So this is gonna be what? This is 1, 2, 3, 4, 5, 6, negative 6. We got 1, 2, 3, 4, 5, 6. We got positive 6. And so when we graph this, we get something of this sort, right? But this is only true when x does not equal -1. So then the question becomes, what happens at -1? What's the deal with negative when x equals -1? Well, we say that it makes the denominator equal 0, but that 0 also appears in the numerator. So you have an indeterminate form, as they say. If you plug in if you plug in -1 into r of x, you get 0 in the numerator, 0 in the denominator. The issue is that you can cancel out the x plus 1s when x does not equal -1, or in other words, when x plus 1 does not equal 0. So to save the suspense, what happens is that it creates a circle. That's it. So it's like saying, yes, r of x is indeed the graph x minus 6. It's just that it's the same only when x does not equal -1. If x equals -1, we say there exists a hole because there is nothing that I can plug in at -1 because I get 0 in the numerator and the denominator. So that's no good. Because of that, at x equals -1, r of x is undefined. So at x equals -1, r of x is undefined. It's undefined. Now, you would think that there is a vertical asymptote, but the problem is that x plus 1 does not just exist in the denominator, it also exists in the numerator. Because of that, there won't be a vertical asymptote. There will be a hole instead. So the hole is at x equals -1. That's the first thing. So this function here is a line with a missing point. So asymptotes, there are none actually. The y-intercept, that's kind of simple because r of x is a linear function when x does not equal -1. So the y-intercept is 0, -6. And then similarly, this is the x-intercept, 6, 0, because we see that on the graph the way it's drawn. The range and the domain becomes this second thing. So domain, we already took care of that because x, when equals -1, we have an undefined function. But anywhere else, the x values are good. So domain is all real numbers except for -6. We skip over -6. And then what's the range? Now, what are the y values? Well, at -1, what would be the range if this was not defined this way where x equals -1 is a problem? Let's say it was filled. Let's say we filled up that hole again. What would it be? What would be the x and y coordinates? It would be -1, -7. But the range here completely skips -7 and moves on everything above -7 and everything below -7. So the range is -infinity to -7 union -7 to infinity. That's going to be my range. And that is the way we graph this kind of function. Now let's look at the next one. It's a similar idea. So the first thing I would do is I would factor the numerator since the denominator is already factored. And when I do so, I want to find two numbers that multiply to 5 but add to 6. So those are going to be 5 and 1. So we got x plus 5 and we got x plus 1. Remember the key observation was that there's going to be holes. The holes occur when you have factors that are in both the numerator and denominator, which is the case here. We have x plus 1, and we have x plus 5, x plus 5. And so therefore, the result is 1 over x minus 3. That's what the r of x is. But what's the issue? This came to be because we canceled out x plus 5, pardon me, and x plus 1 in both the numerator and denominator. So therefore, the domain cannot equal x equals -1, nor x equals -5. So the domain includes all real numbers except x cannot equal -1 and x cannot equal -5. So we know at those points there's a problem. So domain would be -infinity to -5, union -5 to 1, union 1 to infinity. Sorry, it should be -1. Because we're talking about -1. Okay? Now, again, this is true only, the R of x is 1 over x minus 3 only when the domain is not equal -1, -5. These are the holes. These are where the holes occur. So the holes occur at x equals -1 and at x equals -5. So we're gonna have a hole, not an asymptote. There will be asymptotes though, because my function r of x, when you did all the cancellations, resulted in 1 over x minus 3. We know what that's gonna look like. X minus 3, that means that the domain also actually, pardon me, this is not completely true, because the domain also does not include 3. It also does not include 3. So we actually gonna have this kind of domain. -infinity to -1, pardon me, to -5, union -5 to -1, union 1 to 3, union 3 to infinity. So that's my domain. So the holes do not occur at -3. What I have at -3 is an asymptote. So I have a vertical asymptote at x equals 3. So what is x equals 3? Right here. What would be the horizontal asymptote? Is well, because we have this rational function, the numerator has a smaller degree than the denominator, and so the horizontal asymptote is the x-axis. Okay, and so the range we also have to be careful. Again, the range is probably the most intriguing part. We have to be careful for that. Before we get there, though, we want to talk about the x-intercepts. When is the x-intercept? The x-intercept is when the y value is 0, which means that my numerator has to equal 0, but my numerator is just 1, so we actually have none. None. We have no x-intercept, we should know that because the horizontal asymptote is y equals 0, and we only have one vertical asymptote. Now, what is the y-intercept? The y-intercept is when x equals 0, and if I plug in x equals 0, what do I get? I get -1/3 when you plug in 0 into this function, right? And we get here, because it's not none of these, it's none of these, we get here. So then that means that the y-intercept is 0 comma -1/3. So it's going to be here somewhere. Okay. Okay. And now this is when things are a little bit strange. So we are able to figure out no x-intercepts, the y-intercept, the vertical asymptote, the horizontal asymptote, the holes. So we have we have more than one hole, we have holes. Now, if I were to graph this, right, normally, what would it be? Normally, I would have a graph like this. Normally, I would have this, and I would have a happy day because I graphed it, right? That's what I normally would have, but then I have holes. I have holes where? At -1, and -1, 2, 3, 4, and at 5. So actually, I have holes here. And this is where the range comes into play. So, for example, we know for a fact that the range has to be bigger than 0 because we have this whole piece here bigger above 0. So that's part of it. That's a fact. Okay, we know that we have a portion of the interval for the range that it's bigger than 0. However, there's an issue at these um, open circles. So what I'm going to do is I'm going to graph this. So let me just refresh it. My memory, x squared plus 6x squared plus 5. 6x plus 5. So we got x squared plus 6x plus 5. And I'm going to divide that. I'm going to divide that by x plus 1, x minus 3, x plus 5. X plus 1 times x minus 3 times x plus 5. Now when I graph it, we see that asymptote, right? X equals 3. We see the the horizontal asymptote, y equals 0. We know the y-intercept here is at 0 comma -1/3. So we know these things. What we don't know is that hole that exists at -1. Because it's a hole of a point. It's hard for the graph to indicate that. But we do know that there's a value there at -1. And we do know that if I make this, yeah, at -5, there's also another hole there as well. So then what we're going to do is we're going to try to figure out what are the y values for those points at -1 and at -5 if this were to actually exist. So remember, this function is 1 over x minus 3 when the domain is not this, when it's not those x values. So let's first figure out what those would be. So we have a hole at -1. So what would it be if there was no hole? Wouldn't it be -1/4? Because I'm plugging in into this function again. I'm plugging in -1 for x. This is when x equals -1. And if x equals -5, what would it be? Wouldn't it be -1 over -5 minus, sorry, it should just be a positive 1. So this should be -1/8. So at -5, we're closer to 0. And at -1, we're just a bit below -1/8. So then what would be the domain? It would be everything from -infinity to, so you go -infinity all the way to this point. This point here is -1/4. So this is going to be -1/4. And then union -1/4. And so -1/4. I know it's not kind of small, but as you saw in the other graph, this is increasing. So -1/4 all the way to -1/8. So it's -1/8. And then we're going to go from there. -1/8. We go to 0, right? So after we get past this point, we get closer and closer to 0, never actually touch it. and then we go above the horizontal axis, and we go from 0 to infinity. So that was tricky. This range here was tricky. Don't get too alarmed. Not all of them are going to be this tricky, but this one was a tricky one. This one was. Okay. Okay, so these are the cases where we have holes, and these are just, of course, we're going to exaggerate our holes and draw a big hole, but in reality, it's an infinitesimally small point that we call a hole. So we have rational functions that have holes, and these holes occur when we factor the numerator and denominator, we have factors that cancel each other out. That cancellation process indicates that there's no asymptote, but instead that there's a hole at those points. And here we have a situation in the second example where we have a function that is rational, but it has holes at certain places, in this case at -1 and at -5. Okay, so now we've reached the final kind of special case of rational functions. And this is where we have that third case where we have slant asymptotes. This is the case when there is no horizontal asymptote, but instead slant asymptotes. Okay, and so the first thing we should do is to see if we can factor things out. If I factor, I get x squared plus 1, x squared times x plus 1, and we get x plus 2, x minus 2. Do you see here how we don't have any factors to cancel? So therefore, we don't have any holes to even talk about. And then we can immediately find a vertical asymptote. The vertical asymptotes occur when my denominator is 0, x plus 2, x minus 2 equals 0. So then we know that x equals 2 and x equals -2 are vertical asymptotes. So we have two of them. So in this case, we have vertical asymptotes. So we have x equals 2 and x equals -2. So those are my vertical asymptotes. So I'm going to draw that at -2. And at +2. Okay. The x-intercepts are when the numerator equals 0 and the numerator equals 0. When does it equal 0? Well, it equals 0 when x equals 0 or when x equals -1. That's when we cross the x-intercept. So at x equals -1, we got 0. Let me just... Yeah, so at 0, we're at 0. And we are also at 0 when it's -1. So we have these 2 points, right? Asymptote at x equals -2 and at +2. So here we have 0, 0, and -1, 0. I should write this in blue. 0, 0, and -1, 0. And then we have the y-intercept. The y-intercept is when x equals 0. But you notice when you plug in 0, you get 0 in the numerator. So whenever you have the x-intercept at 0, 0, it's immediately the y0, the y-intercept as well. It just comes with it because both of them are zeros. Okay. So what's going to be my domain? That comes directly from the vertical asymptote. It can't be -2 and it can't be +2, but it could be anything else. So we know that this is going to be -infinity to -2 union -2 to 2 union 2 to infinity. Okay. Now we have not spoken about the slant asymptote. And I think I'm going to create I'll have to demonstrate some background knowledge about this. Um, so, what is this slant asymptote? Um, so, slant asymptote occurs when the numerator has a higher degree than the denominator. Okay. So if that's the case, then this is what we have. I'm going to go over here. Okay. So r of x equals x cubed plus x squared over x squared minus 4. So the degree here, the degree of my numerator equals 3. The degree of my denominator equals 2. So 3 is bigger than 2. So there's no horizontal asymptote. No horizontal asymptote. So then we have something that's called slant asymptotes. But what does that even mean? Well, whenever we have a polynomial or the rational function, I should say, if you notice, if we forget about this term rational function, just think about what this actually means. This means x cubed plus x squared is divided by x squared minus 4. So in reality, what we can do, we can use polynomial long division. That's what we can do. So that's what I'm going to do, because I want to show you something. So I'm going to ask myself, what multiplies the x squared to x cubed? X squared, x just x. Then I distribute x cubed, then I got minus 4x. Then what do? I subtract. And then when I distribute that negative sign, I get minus, I get plus. And then the x cubes cancel. And then I continue on, right? I bring down the x squared. This is plus 4x. Then I say plus 1. Then I get x squared minus 4. Subtract. And then when I subtract, I have to distribute that negative sign. So this is going to change everything. This is going to say minus. This will be a plus. Wait, pardon me. Minus. Yeah, it's going to be a minus and a plus. And so then the x squared here cancel. And I'm left with 4x plus 4. Okay. Sorry, I'm timing something. So then 4x plus 4 is my remainder. Why do I stop? Because now my degree is smaller than the divisor. So this is here. This is my remainder. This here is my quotient. And this here is my divisor. Correct? So what can I do now? I can rewrite r of x as x cubed plus x squared over x squared minus 4. I can write this as the quotient x plus 1 plus 4x plus 4 all over x squared minus 4. So r of x can be rewritten as what we get from the division algorithm when we apply polynomial long division. So then you may say, you know what? It just seems like you're making more complicated. But actually now I know a bit more about my rational function. And what do I know? What's the idea? Well, the idea is this. What happens at the ends? So consider the end behavior of r of x. Consider the end behavior of R of x. Now, this idea of end behavior, again, deals with the fact that x goes to infinity. And x goes to negative infinity. Now, this is something along these lines is teetering on what's called limits. So the idea is this: as the x values get really big, if you look at this function now, look at this fraction in particular. When x gets really big, like 100 million, 100 billion, trillion, so on and so forth, as x gets really big, this numerator cannot keep up with the way the denominator is growing. The denominator is growing in a squared way compared to the line. At first, it might not be like a much difference, right? If you plug in numbers that are small, but when you put on numbers that are really big, this becomes extraordinarily big, much faster than the numerator. So because x goes to something that's huge, you know what this goes to? 4x plus 4 over x squared plus minus 4. This approaches 0. And I know it might seem a little strange to be like, how is this possible? You can try it yourself. You can take a calculator and put in numbers that are really big, as big as you'd like. Maybe not too big, but just really big, with something with a lot of zeros in it, and plug that into x, and see what your answer will be when you plug in your calculator. I'm going to tell you it's going to be a number really tiny, really close to 0. So that means that this whole thing goes to 0 as x goes to infinity. So if that's the case, that means that R of x gets really close to the quotient. In this case, x plus 1. This goes for the bottom here, as x goes to negative infinity. So do you see that the end behavior of R of x in this case, this produces the slant asymptote, and the slant asymptote is simply the quotient. So the slant asymptote is the quotient after polynomial log division. So then what is my function approaching? It's approaching the graph x plus 1. So x plus 1 looks something like this. This is the slant asymptote. Slant asymptote is the graph y equals x plus 1. That's all it is. And just to make sure we're doing this on the right track, x cubed plus x squared, right? I'm going to graph it. So let me just move this up here. So we got x cubed plus x squared. And then let me just go back real quick. We got x squared minus, x squared minus 4. So look what we got. You see this? See, so, and you see how this is slant? If you draw a straight line, x plus 1, that's what we get. And so we're going to get something that dips through -1 and comes right back through 0. So we get something like this. We're going to go through. We're going to go through, and then we're going to head right back, and then this is going to go downward. And then what do we have? What do we have in these other corners here? We have looks like the orbit of some kind of comet. So we have something that looks like this. You see, it's stuck in between these two curves. Therefore, these are the horizontal, the vertical, and the slant asymptote. And then we have the same thing going here. We have something that goes up and it goes down. This is when it gets really interesting with this whole asymptotes, slant asymptotes. And the range, oddly enough, because of this inner function here, the domain represents all real numbers. So it's -infinity to infinity. So this is when the range here is not that complicated as you may have thought it would be. But you see the graph is kind of, I like it. It's kind of cool with having these portions being bounded by not just vertical and horizontal asymptotes, but now slant asymptotes. So that's a pretty cool graph of this. And it's the same idea. It's the same idea behind this. So let's try to do this really quick. The domain, so asymptotes, the first thing you can find, vertical asymptotes here, is when the denominator equals 0, which indicates that x equals 1. So x equals 1 is a vertical asymptote for a fact. So x equals 1. And so because of that, the domain is all real numbers except for net 1. So it's -infinity to 1, union 1 to infinity. So we know that. We know that's true. The x-intercept is when the y value is 0, the y value is 0 when the numerator is 0. So the x-intercepts occur when the numerator is 0. If we look at the numerator, it's x squared minus 3x equals 0, which means that x minus 3 equals 0, which means that either x equals 0 or x equals 3 equals 0. So what are the x-intercepts? This is at 0, 0, or at x equals 3. So we know this equals 0 here, and then we got at 3. Okay. 1, 2, sorry. I can count 1, 2, 3. Okay. And so then those are the x-intercept. One is the y-intercept. Well, the y-intercept is when x equals 0. When we figure out when you plug in 0, my numerators go to 0. So we also have 0, 0 as the y-intercept. Okay, so now we're going to go into our slant asymptotes. And to find a slant asymptote, we have to actually divide our function. So we have our function r of x is x squared minus 3x. And this is all over 2x minus 2. So we can do long division here. One thing you can do is you can multiply by negative a half x. So this becomes x squared minus x, and then we subtract it. And when we subtract it, we get minus and we get a plus. So this is negative 2x These cancel, and then you have negative x minus 1. This is negative 2x plus 2. But when you take the negative, you change everything. This becomes a positive. This becomes a minus. And these cancel, and you get negative 2. So again, we don't care about the remainder for slant. We care about the quotient for slant. So my slant asymptote is the quotient. So my quotient will be y equals 1/2 x minus 1. And that's my slant. So we go to negative 1. And then we draw the slant. So at negative 1, we do 1/2. So it'll be from a negative 1, it'll be something like this. Then like this. Then like this. And we keep on going. And I should have drawn with a red color, pink color, I mean. Something like this. So this is going to be my slant asymptote. Y equals 1/2 x minus 1 slant. And just to give us a better idea, it's good to graph. So let's graph x squared minus 3. So x squared minus 3, 3x. And then we got 2x minus 2. 2x minus 2. So when I graph it, look what I get. So at 1, again, at 1, I get something like this. According to this graph, this is what it's telling me, and then I get something like this. I get something of this nature. Something of this kind. And since the range of either of one of these pieces, it goes through all the way downward to negative infinity and all the way upward to positive infinity. So in this case, the range is also negative infinity to positive infinity. It's actually not as complicated as you may think, but that is the range. And I would encourage you to do the homework and see how these rational functions behave and the interesting kinds of behavior that these functions have. So again, we've covered holes, we've covered slant asymptotes, we've covered all the major fundamental concepts and principles of graphing irrational function. So I'll stop with that.